Continuing with vectors, in the last video we looked at how we would take a vector written in the ij form and convert it to a vector given as a magnitude and direction. So now we want to go the opposite direction. So for instance, in a minute we'll do this problem. The magnitude of vector W is 10. The angle of vector W is 55 degrees. Now we're asked what is vector W, but we want to write it in the form, I'll call it AI plus BJ, where A and B, of course, are numbers. So basically, we want to write the vector W in the IJ form. It's given to us as a magnitude and direction. We want to write it as an IJ. So how do we do that? Well, let's just take a quick minute and show you the basis for the little formulas I'm going to give you. We'll sort of use this example. We'll just say, we'll call this the vector W. Now what they've given, just like we've talked about, the magnitude of the vector is actually the length of this, and the angle would be theta. Now we know that we can also write this vector in the form of I and j, and it's based off of this point right here. So what we're going to do is we're going to make this a right triangle. And just for now, just to have a general equation, we'll call this distance x, even though this is the x-axis. We're going to call the distance of the bottom part of the triangle x, and we'll call the distance, sort of the height of the triangle, y. Now if we think about some of our trig functions, for instance, if I think of the cosine of that angle theta, for a right triangle we learn cosine, so ca, adjacent, over hypotenuse, and hypotenuse is this magnitude. Now if I solve this for x, I could say that x is the magnitude of the vector times the cosine of the angle. And this x here is like the I part of the vector. Same thing if I go back here, if I think about this height, or this, we're going to call this y. If you remember the sine of an angle, so opposite over hypotenuse. So the sine of theta would be y over the magnitude of w, or basically the hypotenuse. If we solve this for y, we get the magnitude of w times the sine of theta. And we could think of this y here as the j part of the vector. So we could just summarize it. In this case, I could write the vector W. The I part would be the magnitude of the vector times the cosine of the angle, and the j part would be the magnitude of the vector times the sine of the angle. So you're going to use this a lot, but this just shows you how and where it comes from. And it's actually pretty straightforward. You just take your vector, you create a right triangle, and you go from there. So now if I want to solve this problem up here, I simply fill in what I know. I know the magnitude of the vector W is 10 times the cosine of the angle is 55 degrees. And that's going to be the I part of my vector. And then here, the magnitude again times the sine of 55 degrees. And that's the J part of the vector. And now, if I grab my calculator, and I've actually already done these calculations so I can save some time by just saying this ends up being 5.7i plus 8.2j. And just for fun, I should have, and I encourage you to, although sometimes even I forget, if I were to check and see if this looks like a reasonable answer, let's try and sketch this. 55 degrees, halfway diagonal is 45, 55 is maybe like this. So if that's 55 degrees, and maybe I'll say this length is 10, I'm saying the x or the I part of this, that means that would be like 5.7 here, and maybe 8.2 there. That looks reasonable. All right, so not too difficult. Just have to remember this equation here. Now the nice thing is, if you recall earlier when we were going from the ij vector to the angle and magnitude form of the vector, I had to be careful because we were taking inverse tangents and you had to see where the angle was, and sometimes you had to go find the reference angle. The nice thing is, going from magnitude, direction to the ij, you don't have to be careful about coming up with reference angles and stuff. For example, what if we were given this vector, the magnitude is 5, and the angle is 285 degrees. So that seems like a candidate. That's off in probably the fourth quadrant, and you think, oh boy, that could be something goofy. Matter of fact, if we draw it, make a quick sketch, looks something like this. 285, well, 270 is the negative y-axis, so 15 degrees more, so maybe it's like, maybe right here, where that angle is 285, maybe this distance is 5. Well, the nice thing is, when I try and convert this to ij, I don't really have to worry about anything here. The signs and everything takes care of itself, which is nice. So if I want the vector v, I'm going to take 5 times the cosine of 285 degrees, which is my I part, plus 5 times the sine of 285 degrees, which is the J part. And I've already done the math here. And what I end up with is 1.3i plus a negative 4.8j. And if you look, so we're saying 1.3 is about right here, which looks reasonable, and we're saying down here is negative 4.8. Looks reasonable. And the thing is, I don't have to worry about reference angles and what quadrant am I in. You just plug in the angle and do the math, and you're good to go. So that's nice. All right, one last topic to cover with this vector stuff. Now, what I like to say is sometimes we will have to do math with vectors. So for instance, let me give you two vectors. Matter of fact, let me go back to one of the original ways we defined vectors, just to make sure you don't forget it. Say I'll call vector 2, 5 inside pointy brackets, and maybe I'll call vector W -4, 2 inside pointy brackets. Now say I want to add these two vectors together. It's very straightforward. All you do is you add the x parts, or you could think of this as the I parts, however you want to think about it. -2, and then you add the y parts. Now actually in the book, they go through, and maybe I'll do one quick example how you can actually add vectors graphically. What you do is you draw your first vector, which is 2, 5, 2, 5. So there's vector V. Then what you do is to add on vector W, you start at the tip or at the end of vector V, and then you step off vector W. So in this case, -4, 2, I'm going to go -4, -2, -3, -4, and then 2. So there's vector W, and what happens is when you add them together, so this should be vector V plus vector W, which looks like it's around 2, 7, -2, 7, which is what we have there. I'm not going to spend a lot of time on doing math with vectors graphically, but sometimes I like to do that in the book. So here we added the two vectors. We could have also subtract two vectors. Same idea. So you take the x part of the v vector minus this one. So 2 minus a -4 would be 6. And then 5 minus 2 is 3. So if we try to subtract those vectors, we're going to get 6, 3. You can also, I showed you this before, but oh, let me make this 4. Sorry. 2v plus 4w. So here the 2 and the 4 are called scalars, which I talked about before. And basically, you just take 2 times the v vector. So this would end up being 4, 10. Then 4 times the w vector would be -16, 8. If you add those together, it looks like -12 and 18. All right, so that's a kind of pretty simple math you can do with vectors, especially if it's written like this. And just to show you, of course, the ij is just, I'll just do one of these just to show you it's exactly the same. So we would write v as 2i plus 5j, and the w vector would be -4i plus 2j. So if we add them together, obviously, add the I parts. 2 plus -4 is -2I. Then you add the j parts. 5 plus 2 is 7j, which is a similar kind of thing. So to do this kind of math, when your vectors are in the ij form or even with the pointed brackets, is very straightforward. What's a little trickier is if you are asked to add two vectors together, but you're given the vectors in the form of magnitude and direction. For example, how about here's a vector v, has a magnitude of 5, and the angle is 40 degrees. Vector w, the magnitude is 6, and the angle of this one is 100 degrees. And we want to say we're going to add these together. Basically, we want to add the two vectors together. What does it equal? And we want the answer to be also the same as this, with the magnitude and a direction. As a matter of fact, just to make it more interesting, how about we'll take 3 times the v vector plus 2 times the w vector. So I got to take this v vector, which I know the magnitude and direction, in some way multiply that by 3, and then add it to this w vector multiplied by 2. So what do we think we can do? I mean, is it something like, could I multiply the magnitude by 3 and the angle by 3, and would that be 3v? And then, actually, no, you cannot. You cannot do that. As a matter of fact, there is not a straightforward way to take these two vectors and to perform this math. In fact, what we have to do is, if you have a vector with magnitude and direction, you actually have to convert the vector to ij. So in a minute, I'm going to take both these vectors and convert them to the ij form. And then you do the math. Once you do the math, they're still in ij form. And then the last step, you have to then take that final vector and convert back to magnitude and direction. So it's almost like the only way we can do the math is if the vectors are in the ij form. So we have to first convert the vectors into ij form, do the math, and once we've done the math, convert the vector back to magnitude and direction. So, actually, just for fun, once again, it's always a great idea to make a quick sketch, like what would this thing look like. So basically, it's like we have two vectors acting on the same point, and when they work at the same time, what is the result going to be? So for instance, this vector v is 40 degrees and a magnitude of 5, so 40 degrees maybe is right here. So there's vector v. Vector w is a little bit longer because it's 6, but it has an angle of 100, which is a little past 90. So what would happen if you think of these like maybe two forces, if they're acting on that point? My hunch is, if this pushes like this and this like this, I don't know, my guess is it's going to end up somewhere in between, something like that. So that's the answer we would expect. So how would we do it mathematically? Well, we take the vector v, and I'm going to write it as an ij vector. So you take the magnitude times the cosine of the angle, that's your I. Then the magnitude times the sine of the angle, and that's j. Do the same thing for w, except now my magnitude is 6, my angle is 100. So 6 cosine of 100 degrees I plus 6 sine of 100 degrees j. I guess I could just write equal here. So I did the math here, and I got 3.8 I plus 3.2 j, and I got negative 1.0 I plus 5.9 j. So this is the sort of the new v vector and w vector. But actually what I have to do is 3v, let's actually write what 3v would be. So I'm going to multiply the v vector by 3, and you get 11.4 I plus 9.6 j. And then, how about 2w? I do that because I'm really looking for 3v plus 2w. So 2w would be negative 2i plus 11.8j. So now, if I want to finally add these two together, 3v plus 2w would be 9.4i plus 21.4j. So that's really the answer now as an ij, but since the problem began with vectors written as magnitude and direction, that's how I want my final answer to be. So I now need to convert this back to magnitude and direction. So the magnitude, if I write it like this, of course it's the square root, and it's the I part squared plus the j part squared. And we take the square root of all that, you get 23.4. Of course, the angle is going to be the inverse tangent of 21.4 over 9.4. Now, if you look at this, it looks like we're up in the first quadrant. So when I grab my calculator, it tells me the angle is 66.3 degrees. And that actually looks correct. That's a pretty good guess of what this angle would be. So there you go. A little involved, but just a lot of busy work, not horribly complicated. Now the last thing I want to quickly do is a similar kind of problem that I just did, but there's one twist to it, and it confuses students because it's like a story problem. Sometimes they'll say, a ship is in the ocean. Well, I'll just make one up. A ship is in the ocean, and there are two things that are affecting the direction of the ship and the speed. And that's the wind that's pushing the ship in a certain direction, and then maybe the current of the water or the ocean or the sea. So let's say, here's what they like to do. They will give you the magnitude And we'll say, we'll call V the wind. And I won't even give any units. I'll just give a number like, 12. And now they give you the direction, and here's what they do with the direction, something interesting. They do this thing where they say north 10 degrees west. What that means is, if we were to draw a diagram, north 10 degrees west that means you start north, and north is like up. North is like the y-axis. We would call this almost like a compass, So north is straight up, and then 10 degrees west. So from north, it's saying now move 10 degrees west. Well, west is to your left. So if I move 10 degrees, maybe I end up. So like here's my V vector for the wind. So if this is 10 degrees here, when I do my math, what I really need to know is this angle right here. That's really going to be 100. And then the magnitude of this is 12. So it's like I have this vector, magnitude of 12, angle of 100 degrees. Now say the current, somehow the water is pushing the boat. We'll call the current W, vector W. We'll say it has a magnitude of 6, so it's not quite as strong as the wind. And we'll say that it is pushing the boat south 25 degrees east. So for this one, my direction south is like the negative x-axis, 25 degrees east. And when I draw that vector, it's going to be about half the length of this one. So 45 would be halfway, so maybe this is the W vector. Since this right here is 25 degrees, when I do the math, I need to know this whole angle. So it's really 270 plus 25. When I get ready to do my math, that's actually a 295 degree angle. And of course, the magnitude is going to be 6. So now this becomes just like the last problem. In a sense, I'm adding these two vectors together. And since both these vectors have a magnitude and a direction, the way we're going to add them together is convert both of them to ij vectors, add the ij vectors, and then convert them back to magnitude and direction. But the tricky thing is, at the very end, you're going to get your direction to be some kind of degree angle, but then you have to convert that degree angle back into this directional kind of angle. So let's just go through this real quick. So if I convert V to ij, magnitude's 12, cosine of 100 degrees, that's the I part. The j part is 12 times the sine of 100 degrees. So for W, magnitude is 6, cosine 295 degrees I, plus 6 sine 295 degrees J. Now, I do have to grab my calculator. I have not worked this problem out yet. 12 times the cosine of 100, negative 2.1. Makes sense because you can see that V vector is a little bit in the second quadrant. And then sine of 100 times 12, 11.8. The W vector cosine of 295 times 6, 2.5 I. And then the j part, 295 sine times 6 equals negative 5.4 j. Now, to see the combined effect of the wind and the current, you sort of add them together. In this case, you're going to get 0.4 I plus 6.4 j. So that's my final vector. But now I need to convert it to magnitude and direction. So 0.4 squared plus 6.4 squared and take square root of all that. 6.4, so that's the magnitude of the resultant vector. And the angle, of course, it's the inverse tangent of the y part, or the j part, over the I part. So now 6.4 divided by 0.4 equals the inverse tangent of that, 86.4 degrees. So actually, it ends up being like this. Maybe not as far as 6.4, maybe this far, that direction, when those two get added together. But we're not done. I almost acted like we were done. Because the original problem, the direction was given with these north, west, east, and south. I need to convert that. So if I look at this, I know 86.4 is right here. These directions, you always start with either north or south. So in this case, since I'm closest to the north sort of axis, I would actually say the angle is north, and now I'm going to go east, and I'm going to go 13.6 degrees east. Because basically, oops, wow. See, I did it in my head. It's north 3.6 degrees east. You basically take 90 minus 86.4, 3.6. So there's your final answer. There's the direction. There's the magnitude. All right, not too bad.